nothing like starting off back to math, back with a bunch of properties on a screen, right? So we're going to start chapter 5. Chapter 5 is a continuation of chapter 4. So if you forgot it all before Christmas, it's going to come back to you. I'm sure you guys didn't forget it all, though. We are going to be talking about our basic trigonometric functions once again. So sine, cosine, tangent, secant, cosecant, cotangent, all that good stuff. So just kind of a review before we even kind of jump into these fundamental identities. Let's just kind of review in our own heads. How do we find the sine, cosine, and tangent? So if you want to type in the chat or tell me what the sine of a angle represents what when we're talking about a right triangle. So the very basic definition before we got into all this fancy stuff. So we have a right triangle, right? Okay, and here's our little right angle. Oh, that's not on the right tool. All right, so we have our right triangle. We have an angle. We'll call this angle theta. Okay, and our long side over here is obviously the hypotenuse, right? So if we take the sine, this pen is way different. Oh, okay. Sorry, Sarah. Let me make sure I'm sharing. Can everybody else see my screen? Now can you see it, Sarah? Okay. All right, awesome. All right, so sine of theta, right? Oh, this pen is totally different than my other one. All right, so the sine of theta represents the ratio of our opposite side over our hypotenuse, right? That's our so. And then we have the cosine of theta, which represents our adjacent side over our hypotenuse. Okay, and then we have the tangent of theta, which represents the opposite over the adjacent side. Okay, so that's kind of our way back definitions, right, of what sine, cosine, and tangent are. SOHCAHTOA is kind of the way that we remember, or at least the way I remember it, the way that I was taught it. You might have a different way that you like to remember that. Then we also have our opposite functions, which are listed right here. So you don't have to watch me write them out. The sine of some angle u can also be represented as 1 over the cosecant of u. So that's you're basically flipping 1 over the inverse, right? So, and you can see that written right here. So the cosecant of u is represented as 1 over the sine of u. And then we have this reciprocal relationship with cosine and secant. And I just said that wrong. It's not the inverse, it's the reciprocal. The cosine relationship between the cosine and the secant. And then we have the tangent relationship, which is the tangent and the cotangent. So I think everybody kind of hopefully remembers those. Those are our buddies, right? We also have this relationship that we can kind of derive really quickly. And that is that the tangent of an angle is equal to the ratio of the sine over the cosine. So I think this makes sense if you do just a quick derivation. So the tangent of theta, right, is equal to the sine of the theta over the cosine of theta. And we just said that the sine of theta is the opposite over the hypotenuse. And the cosine of theta is the adjacent over the hypotenuse. And if we do our kind of funny things with fractions where we have this hypotenuse both in the denominators, we end up with the tangent of theta is equal to the opposite over the adjacent, which is what our original property said. So another way to think about the tangent of theta is the ratio of the sine of theta over the cosine of theta. Or we can think of it as our opposite over our adjacent side, right? And so then it follows, since the cotangent is the reciprocal, then the reciprocal relationship remains the same, right? So the cotangent of some angle would be equal to the ratio of the cosine over the sine. Okay. So those, I think, are kind of warm-up properties. I think we've seen all of those properties before, maybe not the quotient ones, but probably have seen those before. We did not talk a lot about these other properties, but we will. We'll do kind of a quick review of those. So we have these Pythagorean identities that we didn't talk a whole lot about, but they have to do with they're just basic identities that have to do with derived from the Pythagorean theorem. Okay, so the first one that's kind of useful is that the sine squared of an angle plus the cosine squared of an angle equals 1. So I always kind of like to just throw these into Desmos because I'm a visual person. So let's see, that's not Desmos. Where are you at, Desmos? Pull a Desmos up here. Everybody okay so far? Your brains are warming up. Okay, and so what this represents, this Pythagorean identity, when you see the sine squared of a number, this is just the way that we write exponents with trigonometric functions. So really what this is representing is the sine of u squared is really what it's representing. It can also be represented like that. We just it with the exponent next to the sign, because if you would just write, this pen is really, really goofy. If you would just write the sine of u squared, then it implies that the exponent belongs to the u and not to the whole function. So this is just kind of the mathematical way that you can write a trigonometric function squared. So you could also write it this way and it's correct. And in fact, when you put it in Desmos or your graphing calculator, you're going to end up writing it like this. So if we do the sine of x, and then we want to close that, and then the whole function is going to be squared plus the cosine of x squared. Nope, if I type correctly, that would be helpful. It's going to be a super exciting graph, right? Because we know that that just equals 1. So you can see here that that represents as 1. So let's just take this apart a little bit. I think it's interesting to see what does the sine and the cosine look like separately. So what they look like separately is we have our sine curve in red. Let me zoom in a little bit here. Okay, we have our sine curve in red and we have our cosine curve in blue, right? And you can see that they're basically exactly opposite of each other. So I don't have, let's put my steps as, there we go. So for example, when your angle equals pi, right, your cosine curve has a value of 1 while your sine curve has a value of 0. And when you add those two together, you get 1. Here, when your angle measurement is pi over 2, then your sine curve evaluated at pi over 2 is at 1, and your cosine curve is 0. So obviously when you add 1 and 0 together, you get 1. And then kind of here we have in the middle, So if our angle represents 3 pi over 4, then you can see the sine and the cosine curve are both evaluated at 1/2. And so obviously 1/2 plus 1/2 equals 1 whole. So that's just kind of, I don't know. I think it's kind of interesting to look at those sometimes. It helps at least me stick in my brain a little bit. So we have that Pythagorean identity, sine squared plus cosine squared equals 1. We also have the identity that 1 plus the tangent squared of u equals the secant squared of u. So let's kind of look at that a little bit. I promise we won't take this long on every one of them. So we have, on one side, we have the secant squared. On the other side, we have the tangent squared. Okay, so you can see this is before I added the 1 onto the tangent, right? So you can see when we graph that these two curves are similar, except the secant curve is shifted up by 1, right? So then it makes sense that if we add 1 to the tangent squared, then we'll end up with the secant squared. Not subscript. Plus 1, there we go. Then we shift our graph up. Now those are the same. And then you'll find the same if you do, there's a relationship between the cosecant and the cotangent. So 1 plus the cotangent squared equals the cosecant squared. Okay. And then the last set of properties that we're going to use. So basically what we're going to do is we're going to take all these properties and then we're going to look at some, we're going to look at a lot of different expressions that have to do with trigonometric functions and see if we can kind of use all of our different identities to simplify or to write in a different form and that kind of thing. So we're kind of going to pile all these together and use them. All right, so these last identities I think are also that we're going to talk about are the cofunction identities. And I think these make a lot of sense if you just look at them. So the first one is that I think especially the sine and the cosine. So the sine of pi divided by 2 minus u equals the cosine of u. So I think this makes sense. We're not talking about the squared functions anymore. We're just talking about the basic functions. If you remember, again, pulling out of your brain, we have our basic sine function, right? And we have our cosine function. And if we just look at the two graphs of these, right? And you look at how they're shifted from the one to the other, yeah, that's the cosine function. The cosine function and the sine function, right, differ by an x component of pi over 2. So the graph, for example, from the sine to the cosine, you could say is shifted by pi over 2, right? So these cofunction identities basically just say that we could shift the sine curve graph, right, to the left, and then that will end up with our cosine function. No, to the right, we're subtracting. So we're going to the right. We could shift our cosine function or sine function to the right, and that will end up with our cosine function. Or we can shift our cosine function, and then we'll end up with our sine function. We can do the same with our tangent and cotangent and our secant and cosecant functions. So they all have this relationship of that we can shift one to basically evaluate what the other function is. All right, who's having fun? Who's excited to be back and be doing trigonometric functions, right? On a Thursday morning. You guys still here with me? Yay, math. Aiden, hey. I thought maybe you would thought. Aiden, I admit I forgot about class this morning too. So I was glad to have a reminder. I was like, oh, it's Thursday morning. Back to a routine. All right, so let's try some of these out. Keep all of these trigonometric identities in mind when you're doing the work. We are not going to use even and odd identities. We can talk about those if you want, but we're not going to be using those for this section. We're basically going to just kind of dive right in there and do some problems. So let's get started. All right, where are my notes at? One of these has my notes. I have way too many tabs. There we go. All right, so let's do some examples from 1 through 14, because 1 through 14 are basically kind of a review from chapter 4. Okay, and maybe I can make this a little bigger so it's not so tiny. Oh, that's lovely. All right, well, hopefully you guys have your notes there. If not, I'll write them bigger because my eyes are not that small anymore. All right, so 1 through 14, kind of, again, just review from where we're at. Use the given values to evaluate, if possible, all 6 trigonometric functions. So you probably felt like you did this a lot in chapter 4, so we're going to warm back up by doing it again. We'll just go ahead and do, it doesn't really matter which one we do. Let's do number 2 to kind of warm our brains back up, right? Oh, this pen. Okay, so number 2 says we have the cosecant of theta equals 2. Okay, and we have that the tangent of theta equals square root of 3 over 3. And we want to evaluate all the other trigonometric functions based off of this information, right? So kind of going to pull this stuff back out of your brains. There's more than one way to do this. One is that you could, I mean, technically, I think the book just wants you to use all of your definitions. I'll be honest, when I started doing this, I just kind of busted out my SOHCAHTOA and figured out what the hypotenuse and the, adjacent and opposite sides were, and then went from there. So there is more than one way to do this. But if we're going to use properties, let's just go ahead and use our properties. So the first thing that we know is that the cosecant of theta is 2, right? So that means that we should be able to use our reciprocal identity and find the sine. So that means that the sine of theta is going to be 1 over 2 because the cosecant and the sine have the reciprocal relationship, right? We have that the tangent of theta equals the square root of 3 over 3. So then we know that the cotangent of theta is 3 over the square root of 3. But we don't like to write square roots in the denominator, so we would write this as 3 square root of 3 over 3, or just square root of 3. So the cotangent of theta would be the square root of 3. So then we have, our last two we have is our cosine. And then what follows from that is our secant. Right? So then we have to do a little bit more work to kind of put this together. So if we know that the sine of theta is 1 over 2, this is where I kind of went back to my, SOHCAHTOA, right? So if the sine of theta is 1 over 2, that means that my opposite side over my hypotenuse, my opposite side is represented by 1 and my hypotenuse is represented by 2. All right? And then if I know, sorry, I'm just thinking in my head. I've done this different ways every time I've done it. If I know that my, we'll go here to tangent, right? Tangent of theta represents my opposite over my adjacent side. So my opposite side is the square root of 3, and my adjacent side would be 3. So I have two different values, right? For my opposite side, I have 1 with a hypotenuse of 2. I should be drawing a picture for this. And I also have that my opposite side is the square root of 3, and my adjacent side is 3. So how can this kind of be? How can I rectify that? Well, that's because my sine and cosecant relationship have probably been reduced, right? So another way that I could write a sine of 1/2 and still have my opposite side be represented by the square root of 3 is that I could write this as the opposite side is the square root of 3, and the hypotenuse is 2 times the square root of 3. Keeping those relationships, okay? So then when I go to do my cosine is my adjacent side over my hypotenuse. So it would be 3 over 2 square root of 3. And again, we don't like that square root of 3 in the denominator, right? So we're going to end up with, I'm running out of space, sorry, secant. End up with 3 times the square root of 3 over 2 times 3, or the square root of 3 over 2. Okay, and then if I'm talking about my secant, the secant is just going to be the opposite of this, the reciprocal, right? So it's going to be 2 square root of 3 over 3. And I am sorry for the mess. I'm going to have to get a better pen. All right, so that was kind of one way to do it. As I'm sitting here talking, I'm thinking, oh, another way that I could have done this, and maybe this would be less messy, is that way back up here, I knew that my sine of theta equals 1/2, right? I knew my tangent of theta equals the square root of 3 over 3. I also know that the tangent, no, that's not what I wanted. The tangent, hopefully I don't run out of room. The tangent of theta equals square root of 3 over 3, which also equals the sine of theta over the cosine of theta. So I could actually plug in here for my sine of theta. I need more room. So square root of 3 over 3. And I know that the sine of theta equals 1/2 over the cosine of theta. It's kind of a funky notation. All right, so then if I do some, let's do our good old proportions. So I can do the butterfly proportions, right? So if I did square root of 3 cosine of theta equals 3 divided by 2, and then I end up with, there we go, the cosine of theta equals 3 divided by 2 square root of 3, which is where we were back up here. And then we can simplify that a little bit. So did I lose everybody on the first problem, or are you like, okay? Or did anybody have a different way that might have even been easier than one of those two ways? Makes sense, Aiden? All right. I think got it. We'll do some more. All right. So let's do like, let's see which one looks fun. Like I said, there's more than one way to do it. So let's do number 12. 12 and 14 are kind of interesting. Okay. Let's just start over. My new pen is super, it writes really well, but it's like, whew, okay. There we go. I should have you guys all tell me something exciting you did over a break. We'll have to do that at the end of class. You guys have to tell me if there's anything exciting you did. All right, so let's kind of, let's do number 12. Okay, so number 12 says the secant of theta equals -3 and the tangent of theta is less than 0. All right, so let's figure out what that means. Okay, so we have the secant of theta equals -3, and I'm just going to put -3 over 1 just to kind of help us out a little bit, right? And then we have that the tangent theta is less than 0. Okay, I'm going to actually do something that I probably should have done in the other problem is just draw a quick triangle too, so that I can visualize where my different values are. Not necessary, but if you're kind of a more visual person, sometimes it can just help to see. And you can just pick whatever theta you want, and your triangle is probably not going to be perfect, but that's okay. So the secant of theta is the reciprocal of the cosine, right? So we know that since the secant of theta is -3 over 1, the cosine of theta is -1 over 3. All right, so we have 2 of the 4, or 2 of the 6 trigonometric functions. We have 4 to go, right? If I wanted to show this on my triangle here, right, I know that the hypotenuse is 3 and the adjacent side is 1. And I know that one of the 2 is negative. Now, the negative seems kind of weird when you put it onto a triangle, but remember the negative just represents the direction kind of on the unit circle. So, but we do need to figure out where it goes so that when we identify our other trigonometric functions, we know, where the negative belongs to. So the trick into figuring out, does the negative sign belong to the 3 or the 1? It lies in our tangent. So we know that the tangent of theta is less than 0. Okay, so if the tangent of theta is less than 0, the tangent represents the opposite over the adjacent. So the tangent of theta is less than 0, so that means it's kind of a negative value. Then I'm going to assume that that means that the 1 is what carries the negative side, not the 3. Okay, the only way that that 1 would be positive is if our opposite side was negative, but we don't have any information that's leading us to that. So it seems to be that our adjacent side is the one that has the -1 in it. Okay. All right, so we have secant, we have cosine. We need to figure out the sine and the tangent and their reciprocals. Another kind of piece of information that we want to pull out from our background is if we have 2 sides of a right triangle, we have the adjacent and the hypotenuse, we can figure out our opposite side using our good old friend Pythagoras, right? So we know that, you guys probably learned it, I was just teaching my son this, a squared plus b squared equals c squared, right? In trigonometry, really, it would be more appropriate to say opposite side squared plus adjacent side squared equals hypotenuse squared. I think that makes a little more sense, but this is kind of the standard way everybody learns Pythagoras. So we have the adjacent side and the hypotenuse side. So opposite side squared plus -1 squared equals 3 squared. And we end up with that the opposite side equals the square root of 8. So it's probably good that we didn't make the opposite side negative, because square roots and negatives, not so fun. So we know the opposite side is -8, right? So then if we want to do the sine of theta, the sine of theta is our opposite over our hypotenuse, so square root of 8 over 3. If we want to do the tangent of theta, that is our opposite over our adjacent, so it's going to be square root of 8 over -1, or negative square root of 8. Okay, and then I'm not going to take the time. You guys know, if you want to do the reciprocals, we're obviously going to flip the numerator and denominator and then have to do some work to get the square root of 8 out of the denominator. Okay. Really quick, I think 14 is kind of interesting. So we won't do all of the trigonometric functions, but we have that the tangent of theta is undefined. I can't even spell it right, even though it's on the sheet. Undefined. We have that the sine of theta is greater than 0. Okay. So what in the world does that mean? So when something is undefined, typically that means that we have a 0 in the denominator, right? And if we go back and we look at our different properties, we know that we can think about the tangent of theta as the sine of theta over the cosine of theta. And if tangent of theta is undefined, that means that our denominator equals 0, right? Because when we have a denominator equal to 0, that's undefined. So we would say that the cosine of theta is 0. Okay. And we know that when the cosine of theta equals 0, that's when the sine of theta either equals 1 or -1. But we have this other hint where we know that the sine of theta is greater than 0. So we know that since our cosine of theta equals 0, that our sine of theta equals 1. And then we can do all the other functions from that. So the cotangent would be 0. The all the other values we can follow from there. Okay, it's all coming back, sort of, ish. So that's all, 1 through 14, that's all through there. Basically, 15 through 38, I think are kind of, this is where we kind of get into the fun of use some different trigonometric functions and see what we end up with. Okay, so let's start off with kind of let's start off with number 18. So let me pull that one up. Oh, maybe I can. Trying to zoom in. There we go. That's what I needed to do. So 1 through 14 is kind of just review of chugging through how to do that kind of thing. This is where we start to kind of get something new, but based off of what we know before. So actually 15 through 26 are all the same. They kind of have a multiple choice. They're giving you a trigonometric expression, and they're basically asking you to simplify this. Okay, so for example, number 18, and this is where it might be helpful to have that first sheet of notes, your fundamental, Well, that's nice. It just told me I didn't have any threats to my computer. Okay, so number 18, we have 1 minus the cosine squared of x times the cosecant of x. And basically what they're asking you to do is, it says match your trigonometric function to one of these. You can see these are all a lot more simple than what I have written up there. So basically we're just simplifying this trigonometric function. Okay, so when I look at this, I notice that, I notice a couple things. 1 minus the cosine squared of x reminds me of the Pythagorean identity, where I have sine squared of x, basically, plus cosine squared of x equals 1. Okay, so this first part, right, we have an identity that says that the sine squared of x plus the cosine squared of x equals 1. Or another way that we could rewrite this is that the sine squared of x equals 1 minus the cosine squared of x. And instead of 1 minus the cosine squared of x in our original expression, let's try plugging in the sine squared of x. Okay, so we're going to take this right here, and we're going to go right through there, and we're going to rewrite it as the sine squared of x. Okay, so see if that helps us out. I also have a cosecant of x, right? Another way to write the cosecant of x is 1 over the sine of x. All right, so now I have the sine squared of x times 1 over the sine of x. So sine squared of x over the sine of x. This is just basically like we're squaring the function. So this actually can be simplified. It's basically like having x squared over x to the sine of x. So this, complicated expression here is another way of saying the sine of x. So technically the answer would be F. That is another way to write that trigonometric function. Be doing a lot of. Actually, the whole rest of the section is just playing with different identities to see how we can simplify. It gets a little more complicated, but okay. So for example, let's do, and did that make sense, what we just did? Cool. I actually think it's kind of fun. Like, I don't know. I think it's kind of like a math puzzle. Who doesn't like a good math puzzle to get back into pre-calc, right? All right, let's do a really quick one. This should be a quick one. We have number 20, which is, I'm not even going to write it out. We have the sine of pi divided by 2 minus x over the cosine of pi divided by 2 over x. Okay, so this obviously is setting off alarm bells, and it's making me think of these cofunction identities. Okay, so I know that the sine of pi divided by 2 minus x is actually equal to the cosine of x, right? And the cosine of pi divided by 2 minus x is actually equal to the sine of x. Okay? And this relationship of having a cosine over a sine, or a sine over a cosine, is another way of expressing the tangent function. But in this case, we have the cosine on the top. So this is another way of saying that this is the cotangent of x. So this can be simplified as the cotangent of x. Voila, right? Okay, so we're going to kind of build here. Let's do number 24. I think 24 is a little bit fun. So 24 is the cotangent of x secant of x. Excuse me. So when you see something like this, you're like, okay, let me break this down into I think for me, when I do these problems, if I can get things into basically the sine, cosine, and tangent, so the basic three, initial trigonometric functions that you learn, then that's the easiest way for me to cross things off, because it's just kind of, that's what I don't know, that's what my brain is used to. So what I mean by that is I see the cotangent of x here, but instead of dealing with the cotangent of x, I'm going to write that as the cosine of x over the sine of x. Okay. And then when I see the secant of x, I am going to rewrite that as 1 over the cosine of x. So I'm basically putting everything back to the original 3 sine, cosine, tangent. And then when I have this, I know that I can cross off my cosines of x, and I get 1 over the sine of x, which is a more simple function, but we call this reciprocal relationship the cosecant of x. So basically, the cotangent of x times the secant of x is equal to the cosecant of x. I think I just said that right. Okay. Fun stuff, right? Okay. So then we get to 27 through 38. Actually, we get through 27 through 44. And if you read the directions, it says, use the fundamental identities to simplify the expression. And then it says, use a table feature of a graphing utility to check your result numerically. And that actually says that from 27 all the way through 44. So what I am going to tell you guys is that if you would like to use a table function to check your work, that is completely fine. And I'll show you how we can do that. If you want to just check your work by graphing the two functions, I'm also okay with that. And it's not something that I need to see in your homework. So if you use a table function or graphing function to check your work, I'm not expecting your homework to have the table copied down or the graph copied down for all those problems. I think it's just more of like, once you do the problems, make sure that you can verify that, that you've transformed them correctly is what I'm asking to see. Does that make sense? So I don't want you killing yourself in the homework for 27 through 44 writing out tables for me. I don't need to see that. Just do the verification on your own and it should be good. Does that make sense? All right, good. All right, so let's kind of dig into these. They kind of just step up. Honestly, 27 all the way through 67, same thing. You're just kind of getting more and more complicated. And actually, all the way through, I'm just looking here. Anywhere it says to use a graphing utility to verify, as long as you're doing that on your own, you don't have to sit there and provide me with a graph. You can just kind of say checked with a graph or just put a check mark, whatever it might be. Okay. All right. So 28 says the cosine, and I forget my Greek numerals or Greek. I don't even know. I just remember theta. So I forget what this guy is called. But we have the cosine of an angle times the tangent of an angle. I should remember what that represents. I'll have to look that up at them. So let's simplify this. We don't really have a choice of where we're going to, but again, let's kind of break it down. Beta? That sounds right, Aiden. I'll go with beta. The cosine of beta, right? We can't really break that down, but we do know that the tangent of beta is equal to the sine now I'm going to call it beta. The sine of beta over the cosine of beta, right? It's a pretty easy one. Let's cross out our cosines and say that this is equivalent to the sine of beta. So then what the book's asking you to do is to verify your result. Basically, they just you want to make sure that you're, transforming it correctly. So if we pop into Desmos and we do we already have our sine curve there, right? And then we have the cosine times the tangent. Okay, so if I am doing this graphically, should make my screen a little bigger. I'm just verifying that the two graphs overlay each other. So you can see that those two graphs are equivalent. We have the sine of x equals the cosine x times the tangent. And then we can also convert this to a table and convert this to a table. And you'll see when you look in your table that the values are also the same. So I think, like I said, I don't need a printout of every time that you verify that works. I believe ya. Okay, so 27 through 38 kind of start off with those. Let's kind of jump into some little more complicated ones since we only have like 9 minutes left here. Let's do like some of these in here. And I will admit, number 48, that your brain is just not. I finally solved number 48, but I did 48 like 3 different times, 3 different ways. And I was like, oh, why? Because there's more than one way to get there, right? On some of them, it's pretty obvious the way to get there. But 48, man, I won't make you guys sit through that. But I do have the solution finally. But it took a little bit. So let's go to 40 since you don't want to see me have to go through that all again. I know. Sometimes there's just this one problem, Aiden. You're like, why is this not working? It's like even with factoring, you're like, I know this factors. Okay. These are a little different. They actually are telling you the solution, but you're kind of doing the same thing. It says verify the identity algebraically. Use the table feature to check your result. So they're telling you that what they want you to get to. So the secant of theta minus the tangent of theta times the cosecant of theta plus 1 equals the cotangent of theta. So they're telling you what they want to get through, but you have to actually prove that it's true. All right. So we want to show that the left-hand side equals the right-hand side. The right-hand side has already been simplified for us. So we're basically going to go and do a lot of work on the left-hand side. Okay. So we have number 40 has the secant of theta. No, don't want a parenthesis there. Speaking of secant of theta minus the tangent of theta. So I'm basically working with the left-hand side to make it look like the right-hand side, right? Is what I'm trying to do. They already tell you it's true, but you got to figure out how to get from one to the other. All right. So the first thing I'm going to do is I'm going to convert everything into cosine, sine, and tangent, just because that way it's clean. When I do my multiplication, I know it's good. So the secant of theta is equivalent to 1 over the cosine of theta minus the tangent of theta, which is the sine of theta over the cosine of theta. Okay. And then I have multiplied by the cosecant of theta, which is 1 over the sine of theta. And then I have my good old plus 1 down here. I'm just going to leave that. I think I'm just going to leave that as 1. You could, put 1 as the sine of theta over the sine of theta or cosine of theta or cosine of theta, but I don't really know what I want to do yet. So I'm going to leave that as 1. All right. So now I have, I've got to use FOIL, right? I've got, 2, my brain's totally blanking. 2 elements in each of my parentheses that I need to multiply everything in the parentheses by each other. So in order to multiply this out, I'm going to need to use FOIL. So that should be fun, right? So my first term is going to be 1 over the sine of theta cosine theta. Okay. And then my outside is going to be plus 1 over the cosine theta. My inside term is going to be minus the sine of theta over the cosine theta sine of theta. Oh, I'm totally going to run out of room. Thank goodness I can just extend my paper. Wouldn't that be nice when you're doing math problems? Okay. And my last term is going to be minus sine of theta cosine theta. Okay. So I noticed something about my middle term here. It's my inside term, my third term here. And that's that I have a sine of theta over a cosine sine of theta. So I can cross this guy out, right? And this is positive 1 over cosine of theta, and this is negative 1 over cosine theta. So that cancels each other out. So yay. I'm down to just 2 crazy terms. So I have 1 over the sine of theta cosine of theta. Okay. Minus the sine of theta over the cosine of theta. Right? I do everything right so far? I'm just double checking here. Yep. Okay. So how am I going to combine these terms together? I have 2 different denominators, right? I have the sine of theta, cosine theta, and I have the cosine of theta. So what if I multiply the second term by the sine of theta over the sine of theta? Right? Then I end up with at least my denominator is the same, and I can simplify all into one expression. All right. So that means I will have 1 minus the sine of theta times the sine of theta is the sine squared of theta over the sine of theta cosine theta. This actually makes me happy because this relates to my good old Pythagorean identity, right? So I have the sine squared of theta plus the cosine squared of theta equals 1, or I could rewrite the numerator as the cosine squared of theta over the sine of theta cosine theta. Okay, I am almost there, guys. So I have a cosine theta, a cosine squared of theta in the numerator, and a single cosine in the denominator. So those are going to cancel out like that. And I'm going to end up with the cosine of theta over the sine of theta, which is another way to write the cotangent of theta. So all that, and way back up here, we said that expression equals the cotangent of theta. That was fun, huh? So that is kind of, we're done. There's only 2 minutes left. That's kind of what you're going to be doing. You can try, I mean, I think you can definitely do up through 44. I think that you probably have enough knowledge actually to finish the whole section. So basically your homework this week is to work on 5-1. If you get to some of the higher ones and 5-1 and they're not clicking for you, then just wait. We can go over next Thursday. So we don't have class next Monday. It's just basically this week and next week to kind of warm our brains back up. So if you get to one and you get stuck, you can save it for class. We can do it next week. But I think you should have you have all the properties and identities. Basically, it's just going to get a little bit more complicated and a little bit more messy. So go ahead and try those this week. If you have any questions, send me an email. Thank you guys for coming today. I know it's not exciting, but it's good to get started, and I appreciate it. So, anybody have anything exciting over Christmas break? Oh, you went to Florida, Aiden, and you came back? Oh, cool. You guys did a lot of cool stuff. Aiden went to Florida. Jennifer went ice skating at the fountain at Kings Island, which I totally wanted to do and never made it there. And Adam went to Missouri, right? Mo is Missouri, if I remember my abbreviation right. And Sarah, skiing. Nice. Sarah, I'm guessing you had your siblings from college, your brother from college, I think you said. Yeah. So that's exciting. Awesome. Well, I can't wait to see you guys in person. Thank you for coming. I'm sure it was hard to get on this morning. Um, but again, I think it's just good to get started. So let me know if you have any questions. If not, I'll talk to you guys next Thursday morning. Bye, guys.